All right. All year long, we're going to be doing problems similar to this. That they have all of the AP problems back to a long time. I don't remember what year, 1998 maybe. We will do most, if not all, of those problems. Some of them we'll do on the homework. Some of them we'll do in class like that. Let's take a look at how this problem is scored. This one was out of 15. They're always either out of 15 or out of 10. Obviously, it said like numbers 1 through 4. You said 17 minutes on 5 and 6. You said 11 minutes on 1 through 4 was the ones out of 15, and then the other 2 were out of 10. Right. Part A this year, not this year, but in 2006, was worth 3 points. Should be pretty easy to affirm all 3 of those points. The first one for drawing a line that is close to all the data points. You draw a line that's not close to the data points. That's first. Going through most of the data points, smooth curve, so don't just play connect the dots. Right? Smooth curve is going through this. Non-linear, so it shouldn't be a straight line. Concave up, you don't know what that means yet, but that means it kind of opens up like that. Everybody gets 3 out of 3 on that? We're wrong. All right. Should be easy to earn those 3 points. Scrolling down part B. You didn't necessarily need to write the equation. It's worth 2 points for identifying the pair of quantities that will yield a straight line. You can either do d and t squared, that's the one you probably did, or root d and t would also give you a linear relationship. Hopefully we got both of those points since we did a lab that was almost identical to that last time. Everybody 5 out of 5 so far? Okay. Part C, 4 points. As we talked about before, make sure you always label your axis. You always scale your axis. You show what each tick mark is representing. Maybe not each one, but we're showing where point 1 is, point 2, point 3, point 4. Showing it on the vertical axis. Labeling what that represents. So the horizontal one represents t squared, measured in seconds squared. The vertical one is distance measured in meters. So it's 1 point for the horizontal axis, 1 for the vertical axis. 1 point for reasonably correct plotting of the data. Could be a because your data point should be correct. And then a straight line through the data point. These are straight edges, the side of your calculator, you don't have one, but on the AP basis, draw a straight line. Again, it's pretty easy, 4 points, I think. Especially if you can identify the 2 variables, t squared and d, that give it a straight line. And part D, these were 3 points. Determining the slope, we should get the slope to be about 4.9 meters per second squared. 1 for writing a relationship between the slope and g. 1/2 g is then equal to the slope. You can use a, would be fine. And then 1 point for the answer. Your answer should be somewhere between 9 and 11 meters per second squared. If I get exactly 9.8. 4.88, then times 2 to get the g value. Everybody get something in that range from 9 to 11. Good, good. And then part E, what part E asked about? Ways to improve. Yeah, this is an old AP problem. This is right off the 2006 test. So yeah, it's very well good. Oh yeah, that's why it says example. This is an example of what you could do. Do several trials for each value of B and take averages. I know when you get turned in your lab, that's what a lot of you said, to do something like that. Reduces the random error. Yeah, that's one example of how it could be. It needs to be a specific improvement and how explaining why or how it would improve the answer. On a problem like this one, since it's Form B, what they do every year is there are almost everybody takes Form A, and then also they have a Form B that some students take. Why do they take? Why is there a Form B? Yeah, but most of the people on the West Coast actually take Form B, right? With communication the way it is now, that somebody could take the test in the morning on the East Coast, and then send some of the information, whether we answer or what's on the thing in the West Coast. So there's always two parts. They always release the national average for the A part and not the B part. So this was on Form B, so I don't know what the average was. But on a problem like this, actually most problems, the national average is no more than half. So 7 or 8 out of 15 isn't bad. Obviously, hopefully we did real well since it was almost identical to what our lab was. All right. But there's going to be stuff on the AP that you should or even point. Even if you struggle with like the straight line relationship with variables, once you get like 3 or 4 points just for kind of half a brain. Anybody can connect those points with the curve, right? Well, 3 points right there. You're halfway to the national average, probably. It doesn't require much thought to do that part. Any questions on that? Anything we need to talk about? Excellent. Go ahead, grab your notes. We need to continue working on what we did last time. You might want to get out your student notes, the problems as well. We talked friction last time, but we did not get to the incline problem. So that's where I want to start today. All right. So the problem we didn't do last time was objective 3, trying to solve analytical problems that have the normal force. They will always have the normal force in the problem. Most of the time, they will have a frictional force. Every once in a while, our problems will say that it's based on a friction with a surface. So I guess we don't necessarily always have to. Example 10 states that we have an object sitting at rest on an incline, 30-degree incline. Or asked for the normal force and the frictional force. Remember, all these problems are written out on your student notes. So we have a 30-degree incline. Let's get that in here real quick. We have an object sitting on that incline. Remember, 3-body diagram to label the object at this point. What kinds of forces are acting on that object? Gravity pointed in which direction? Straight down. Good, so this object wants to slide down the incline, right? So we have a force pushing up the incline. What do we call that force? Not normal. Friction. Friction's pushing up, right? We do have normal forces, right? Not straight up. Perpendicular to the incline, right? Remember last time we defined normal force? Normal force is defined as the contact force perpendicular to the incline. Or perpendicular to the surface of contact. All right, we're going to split our forces into X and Y components. If I do it like normal and call this direction X and this direction Y, would gravity be in all the X and all the Y, or have components in both? This gravity, just talk about gravity right now. All X, all Y are components in both. All Y, right? Okay, which that's good because then we don't have to use sine or cosine or anything. What about friction? Both. What about normal force? Both. Notice we have two that are both, right, and only one that's all in the y, which is why we're going to rotate our axis. That's the normal force that way, gravity down. What we're going to do on these incline problems, since this is always going to be perpendicular right here, we're going to rotate that axis around. We're going to call this way the positive x, and this way the positive y. Now notice friction is all in the x. Normal force is all in the y, right? Gravity does have an x and a y component, so we are going to need to split that one up. But now we only have one we have to split up instead of two. Does that make sense? All right, so we have, let's list out our forces. We have gravity, we have normal force, we have friction. And we're going to add those together to get our net force. Any of them have any components of zero? Yes. Which one? Now, normal force. Normal force has an x component of zero, right? Because it's all in the y. And frictional force has a y component of zero. Look up net force. Either of those zero. Well, x, sorry. Yeah. If it's at rest, what's the net force acting on the object? If it's at rest, it's not moving, right? Isn't there no net force? I was going to say that before when because the XD is up by friction and normal force. We're just going to cancel the y component. Yep. Yep. If it's at rest, the x and the y components are zero. What if it's moving, but moving at a constant velocity? It says it's sliding down the incline at 5 meters per second. What would the net force be? Not 5. Constant velocity. What's the acceleration? Acceleration is zero, right? If it's not speeding up or slowing down, acceleration would be zero. Therefore, net force would be zero. Acceleration times mass gives us force. One zero, the other zero. So constant velocity, we would also have x and y components of zero. If it's accelerating, we'll take a look at one like that. All right. So everybody okay before we build in our zeros? All right. What we want to do now is split the force due to gravity into its x and y components. So we have a 3 kilogram object. I'm going to draw gravity a little bit bigger here. The force due to gravity, how would I get the force? Mass times acceleration. All right. Acceleration due to gravity is 9.8. I realize it's zero for the whole problem, but if we're just looking at gravity, 9.8. So this side would be 3 times 9.8, right? 29.4 minutes. Since that's not all in the x or the y, we're going to use sine or cosine to split that up. Notice this way is my x, right? And this way is my y. There's my right angle right there. Very much on the right. What would this angle right here be? Yeah, 60, right? Everybody see that? My incline is 30 degrees. This is the right angle right here. So that should be 60 degrees. So notice my x should be 29.4 times cosine 60.